So, hello everyone, good morning. Good morning. And this is lecture number 11 of the vector analysis, and we are going to start Green's theorem in this class, right? So far, we have completed two topics on vector analysis. The first topic is gradient, divergence, and curl. Next topic that we have completed is line integral, surface integral, and volume integral, right? So, if you have seen that video, then the next three theorems that we're going to see, that is Green's theorem, Gauss divergence theorem, Stokes theorem. All three are very easy to evaluate if you know how to evaluate line integral, surface integral, and volume integral. Right? Super. So in this class, we're going to start the Green's theorem. So first we will define what's the Green's theorem, and then we will directly get into the problems. Right? So okay. So if you have joined Telegram group, so join the Telegram group. So already we have conducted test 1, and that is based on the topic gradient, divergence, and curl. Test 2 is scheduled on Monday evening. This is on line integral, surface integral, and volume integral. So if you want to get question papers and evaluated answer keys, join the Telegram group, right? Okay. So we will start this class. So first we will state Green's theorem. After that we will do the problems, right? Okay. Our voice is audible. So we will state Green's theorem now. Then we will Green's theorem. Right? So Green's theorem. So let R be the closed bounded region in the xy plane. Let R be the closed bounded region. R be the closed bounded region in the xy plane. The xy plane whose boundary C consists of let R be the closed bounded region in the xy plane where the boundary C consists of finitely many smooth curves. Finitely many smooth curves. Let M and N, very important. Let capital M and capital N. Let capital M and capital N be the continuous functions. Of x and y having continuous partial derivative. Having continuous partial derivative dou m by dou y and dou n by dou x in R. Then what Green's theorem says is, right, double integral over R dou n by dou x minus dou m by dou y dx dy is same as the line integral m dx plus n dy. That's it, right? That's what Green's theorem says, right? So this is nothing but your f dot dr, right? This is nothing but your f dot dr, because we know dr is dx I vector plus dy j vector, and if you make a dot product with this, you will have some function. M is a function of x and y, right? Here m and n be continuous functions of x and y. So m is a function of x and y, n is a function of x and y. This is what Green's theorem says, very, very important. So you can see there is a relationship between this double integral and this line integral. You know how to evaluate this double integral, you know how to evaluate line integral. You have to, in question will be like, yeah, verify Green's theorem. They will give a function, right? They will give a function. So you just have to find LHS, you have to find RHS, and then you have to prove that both are equal, right? So this is what Green's theorem says, that the double integral over R dou n by dou x minus dou m by dou y dx dy is same as a line integral m dx plus n dy, right? So this is what Green's theorem. We'll directly get into the problem. So both are equal, right? This is we are evaluating both the surface and this is line integral. So these two are equal. That's what Green's theorem says. So we will do some problems and it is easy to understand. As of now, you by heart this theorem statement. Double integral over r dou n by dou x. You can see from the assumption itself, this first order partial derivative exists, right? So that is m and n are functions of xy and having continuous partial derivative dou m by dou y and dou n by dou x in r, then this will happen, right? Okay. We'll directly get into the problems. Okay. So we'll get on to the first problem. So verify Green's theorem. Verify Green's theorem. The plane for closed curve. You can see this means the closed region, right? Closed curve. So if I put round here means that the C is closed, right? The C is closed. Okay. Actually, we are defining Green's theorem in the plane, right? Plane XY. So verify Green's theorem in the plane for integral over C. So the first problem that we're going to do is xy plus y square, xy plus y square dx, x square dy, where C is the closed curve of the region, that C is the closed curve of the region y is equal to x and y is equal to x square, right? So we'll do this problem. So very easy problem. You just have to verify Green's theorem. That means you need to prove this LHS and RHS both are same, right? Okay. So you can see we need to evaluate. You just have to to evaluate this. We need m and n, right? So we need m and n. So if I know m n, we can find dou n by dou x. We can find dou m by dou y, and we can integrate this. So first you need to find m n. That we can get from the question, right? You can see m dx plus n dy. No. So only Green's theorem will be covered today, right? Green's theorem itself will take 2 classes because I need to do lots and lots of problems on Green's theorem because this is very important. So today's class and next class all based on Green's theorem only. Okay, so you can see you just compare this. So you can see this is m dx plus n dy, right? So you can get m and n from the question, right? So you can get m and n from the question. So first we will draw the diagram, right? So first we will draw the diagram. So we have y is equal to x square, right? So y is equal to x square, nothing but open upward parabola, right? Open upward parabola. This will go on and on like this. Now y is equal to x. So this is a line, y is equal to x. Right? So this is the region we need to evaluate, right? So verify Green's theorem in the plane for integral over C of xy plus y square dx plus x square dy, where C is the closed curve, y is equal to x and y is equal to x square, right? So this is what we need to evaluate. Now first we will find the point of intersection, right? So what is the point of intersection here? So clearly origin is one point of intersection and this point will be 1, 1, right? So to find the point of intersection, so we have y is equal to x and y is equal to x square, right? So to find the point of intersection, so we have y is equal to x and y is equal to x square. So you just solve this. That means x square is equal to x. So x is equal to 0 or x is equal to 1, and we know y is equal to x square. So 0 square, 1 square is 1. So therefore this point is 0, 0 and this point is 1, 1, right? So 0, 0 and 1, 1 is the point of intersection. Okay. Now we need to, what we need to verify to prove. So what we need to prove is, we need to prove that double integral over R dou n by, I can see it is dou n by dou x minus dou m by dou y dx dy is equal to integral over c m dx plus n dy, right? So first what we will do is we will find the line integral, right? First we will find the line integral, and then we will find this double integral, and then we will say both are equal. So first we will find this. Now you can see, to evaluate the line integral, first we will evaluate integral over c m dx plus n dy, right? So we have already evaluated these types of problems, right? Integral over c m dx plus n dy. So first we will evaluate this. So this is same as integral, closed integral over c xy plus y square xy plus y square dx plus x square dy, right? Okay. Now this line integral, right? So let us call this as c1 and call this as c2, right? So c1 c2. So this is nothing but integral over c1 plus integral over c2, right? Now we will evaluate c1 and c2. So to find integral over c1 m dx plus n dy. Now along c1, right? So along c1, you can see what is our this is the curve y is equal to x square, right? So along the curve c1, y is equal to x square. So we will convert everything in terms of x. So that means dy is equal to 2x dx, right? 2x dx. So therefore we are converting everything in terms of x. That means we need to vary x. So x varies from, so for c1 you can see x varies from 0 to 1, right? X varies from 0 to 1. So therefore integral over c1 xy plus y square dx plus x square dy is equal to x varies from 0 to 1 xy plus y square. So x into, and we know y is x square plus y square, and we know y is x square into dx plus x square, and what is dy? Dy is 2x dx, right? So we will evaluate this. So this is nothing but integration of x varies from 0 to 1 x cube plus x power 4 plus 2x cube dx, right? This is nothing but 2x cube plus x cube is 3x cube. So 3x cube plus x power 4 dx. This varies from 0 to 1. So 3 times x power 4 by 4, 0 to 1. And this is x power 5 by 5, 0 to 1. This will be 3 by 4 plus 1 by 5. So this will be, if we take LCM, 15 plus 4. This will be 19 by 20. So 19 by 20 is our integration along C1. Now along C2. So along C2. Now we can see along C2, this is nothing but y is equal to x, right? So along C2, we have y is equal to x. That means dy is dx. Again, we are converting everything in terms of x. That means we need to vary x. So x varies from, so here you can see x varies from 1 to 0, right? So because the direction is very important. So from 1 to 0, we are approaching from year to year. So that means x varies from 1 to 0, right? You don't put 0 to 1, it is 1 to 0. So therefore, integral over C2 xy plus y square xy plus y square dx plus x square dy is equal to x varies from 1 to 0 xy. So x into y is x plus y square dx plus x square, and what is dy? Dy is dx, right? Dy is dx. Will be integration of 1 to 0 x square plus x square plus x square dx, right? This is nothing but 3x square. So integration of x square is x cube by 3. So 1 to 0. 3 will get cancelled. So we will have 0 minus 1, which is minus 1. Therefore, integral over c m dx plus n dy is equal to is equal to integral over c1 m dx plus n dy plus integral over c m dx plus n dy, right? The first curve is first integration is 19 by 20. That is 1. So 19 minus 20 by 20. So minus 1 by 20 is our line integral, right? So this answer is minus 1 by 20. Right? Now we need to evaluate the double integral over r dou n by dou x minus dou m by dou y dx dy, right? You know how to evaluate double integral, right? So we'll do this. Now for LHS, so double integral over r dou n by dou x minus dou m by dou y into dx dy, right? Into dx dy into dx dy. I think there are lots of shades falling in the glass. Stop shade. Need to improvise them. Okay. Okay. So we need to evaluate this. So we have here what's our m here? So m dx plus n dy, right? So m dx plus n dy, xy plus y square is your m. And what is n? M dx plus n dy, it is x square. So we need dou n by dou x. So dou m by dou y, because we need dou m by dou y. With respect to y, you need to differentiate partially. So this will be x is constant, this is y, this is 2y, right? So x plus 2y is your dou m by dou y. Dou n by dou x will be 2x, right? It will be 2x. So with partially differentiating with respect to y. So yes, okay. So therefore, this will be integral over r dou n by dou x is 2x minus dou m by dou y is x plus 2y into dx dy. So double integral over r. So 2x minus x is x. So x minus 2y dx dy. Now we need to find the limits, right? So you know how to find limits, right? You treat one as constant, other as variable. That is, you need to vary. So what I'm going to do is, I'm going to vary x from 0 to 1, y from x square to x, right? You have already done many problems on surface integral. You can also vary, like where y varies from 0 to 1, and you can also vary x from y to root y. X varies from y to root y. You can also do like that also, right? But I'm varying x varies from 0 to 1. X varies from 0 to 1, and y varies from x square to x, right? So you can see x square to x, y varies from 0 to 1. Then only you can cover the inside regions, right? If you take x varies from 0 to 1, y varies from 0 to 1, you can cover only the boundary, right? You cannot cover the inside region. Means you need to take one varies from 0 to 1, other as variables. Then only you can cover the inside regions, right? Therefore, this is the limits now. So x varies from 0 to 1, y varies from x square to x. So 0 to 1, x varies from 0 to 1, y varies from x square to x minus 2y dy dx, right? No problem. So we can shift this. So first we are applying the y limits and then x limits. This will be integration of 0 to 1 with respect to y. This will be xy minus 2y square by 2 x square to x dx, right? So you just put upper and lower limit in place of y. So upper limit will be x into x minus x square minus lower limit is x into x square minus x power 4 dx, right? So just putting upper limit minus lower limit, right, in place of y. So x into x is x square, this is x square minus lower limit x into x square minus x square whole square will be x power 4. This will be 0 to 1. This will get 0, right? This will get 0. So here we will have minus x cube minus x power 4 dx. This is same as x power 4. Same as x power. If you take minus inside, this will be plus, this will be minus x cube dx. Will be x power 4 is 1 by 4 minus 1 by 3, right? Power 4, sorry, integrate this. So integration of x power 4 will be x power 5 by 5, 0 to 1 minus x power 4 by 4, 0 to 1 So 1 by 5 minus 1 by 4. So this will be 4 minus 5 by 20. So which is again minus 1 by 20. So therefore both are equal, right? So therefore both are equal. So therefore Green's theorem is verified. You can see how easy it is, right? So since you know how to evaluate line integral and double integral from the previous classes, the next three theorems are just going to be very easy, right? To verify Green's theorem for this plane, so what Green's theorem says is integral over C m dx plus n dy. You need to integrate line integral. This is surface integral. This is surface integral over surface, right? Double integral. So dou n by dou, you need to find dou n by dou x, dou m by dou y. So you find the limits appropriately. Then you need to evaluate this integral. Then these are very easy to do, right? So we'll move on to the next problem. Is there any doubt? Let's say take this Green's theorem. So we're going to do lots of problems based on verifying the Green's theorem. So verify Green's theorem. So verify Green's theorem in a plane for. So they are given the they are given the curve to be verify Green's theorem in the plane for integral over C x square minus 2xy square minus 2xy dx plus x square y plus 3 dy, where C is the boundary of the region, where C is the boundary of the region bounded by defined by y square is equal to 8x and x is equal to 8. So in the previous problem they were given y is equal to x and y is equal to x and y is equal to x square. So instead of these two curves they are given these two curves, right? So first we draw the diagram. So y square is equal to 8x. So it is an open rightward parabola. And x is equal to 2. This is a line x is equal to 2. The line x is equal to 2. Passing through. So first what we'll do is we'll find the point of this point of intersection. So first we'll find the point of intersection. So to find point of intersection, right? So we have y square is equal to 8x and we know x is 2. Substitute this here. So that means y square is equal to 16. That means y is plus or minus 4. So y is 4. X is, sorry, y is 4 or y can be minus 4 and we know x is always 2, right? Therefore this point will be 2 comma 4. Point is 2 comma 4 and this point will be 2 comma minus 4, right? Because it's a line passing through 2. So 2 comma 4 and 2 comma minus 4. Okay. This is the point of intersection. So this is a curve for C1 and call this as C2, right? So first we will find line integral. So first what we need to do, we need to verify double integral over R dou n by dou x minus dou m by dou y dx dy is equal to integral over C m dx plus n dy, right? So first we will evaluate this curve. So first we will evaluate integral over C m dx plus n dy. This is the same as the curve C1 plus integral over the curve C2, right? So what I'm doing is C1 is this entire curve parabola and C2 is this line, right? So this is the curve y square is equal to 8x and this is the line x is equal to 2. Okay. So first we will evaluate integral over C1 m dx plus n dy. So integral over C1. So what is m dx plus n dy? It is x square minus 2xy dx plus x square y plus 3 dy, right? So along C1, you can see along C1 y square is 8x. So you can see this x is linear. So I'm going to change everything in terms of y. So I'm going to differentiate. You can also differentiate with respect to y also, x also, but I'm going to differentiate with respect to y. Therefore, this will be 2x. This will be 8 into dx by dy. Therefore, this 2, 4 will get cancelled. So we have y is equal to 4 into dx by dy. Therefore, dx is equal to y dy divided by 4. So I'm converting everything in terms of y, right? If you differentiate with respect to if you differentiate with respect to x means you will have 2y dy by dx is equal to this will be 8. So therefore, you can also from here this 2 4 will get cancelled. So we will have y dy is equal to 4 dx, right? You can also convert dx. Okay, with respect to y we are doing, right? With from this you can also evaluate that is what I'm you already seen line integral, right? So you can convert everything in terms of x or everything in terms of y, right? Okay. See, we are evaluating this line integral, right? So when we add up that will be closed, right? When we add up that will be closed. Okay, so in order to evaluate this, okay, if you want, you don't put this closed curve here. C1 and C2 are not closed, but when you add it up, it will be closed, right? If you want, you can do. You don't need. You don't put symbol here. Okay. So I'm converting everything in terms of y. So therefore, y varies from. So you can see the curve in this curve. Y varies from -4 to 4. -4 to 4. So therefore, this integral will be y varies from -4 to 4. X square minus 2xy dx x square y plus 3 dy. This will be y varies from -4 to 4. We are converting everything in terms of y, right? Okay. So x is y square by 8, right? So x is y square by 8 whole square minus 2 y square by 8 into y, and dx is y dy by 4 plus x square be y square by 8 whole square into y plus 3 dy, right? So we are converting everything in terms of y. So this will be integration of -4 to 4. So y power 4 by 64. So y power 4 by 64 to y cube by 8. Right? So minus 2y cube by 8 into y dy by 4 plus integration of -4 to 4. This will be y square whole square will be y power 4. Y power 4 into y will be y power 5. So y power 5 by 64. Y power 5 by 64 plus 3 dy. I'm just integrating, right? Very simple. Here we have whole bracket. So now this will be, if I take this 4, if I multiply this y by 4 here, it will be integration of -4 to 4 y power 5 by 4 into 64 dy minus 2 by 8 into 1 by 4 integration of y power 4 dy, and here we will have integration of y power 5 by 64 and integration of 3 dy 4 to 4 minus 4 to 4 minus 4 to 4, right? This will be 1 by 4 into 64 y power 6 by 6 and this will be 2 1s are 2 2s are. So we will have 1 by 16 y power 5 by 5 integration of minus 4 to 4, and here we will have 1 by 64. I can take this outside. So here we will have y power 6 by 6 minus 4 to 4, and this will be integration of 3 dy minus 4 to 4, right? I think you can evaluate this, right? You can evaluate this. See, this will be 0, right? Because 4 power 6 minus 4 power 6. This is an even function. So this interval will be so this is an odd function here. This interval will be 0. So when you put upper limit minus lower limit, we will have 4 power 6 minus lower limit minus 4 whole power 6. That is same as 4 power 6. So 4 power 6, 4 power 6. So therefore, this entire term will be 0. Entire term will be 0, and this entire term will also be 0. Right? So we will have only this term and this term. Therefore, we will have 1 by 16 into 5. So here we will have 4 cube minus 4 whole cube. And here we will have 3 times 4 plus 4, right? Upper limit minus lower limit. So we will have 1 by 16 into 5. So 4 cube is what? 4 cube is 64, right? 4 plus 16. Yes, we will have 64 plus 64. So we will have 128 plus 3 into 8. So we can cancel the 16 tables, right? Okay. So 4 4s are 16, 4 3s are 12, 4 2s are 8, 4 1s are 4 8s are. So we will have 8 by 5 plus 24, right? So 8 plus 24 into 5 divided by 5. So 8 plus 24 into 5 will be 120 by 5. So we will have this to be equal to 128 by 5. So 128 by 5 is our along the curve C1, right? Now we will find along the curve C2. Now along C2, we need to evaluate integral over C m dx plus n dy, right? Integral over C m dx plus n dy. So this will be integral over C, integral over C2, right? So what is m dx plus n dy? It is x square minus 2xy square minus 2xy dx, x square y plus 3, x square y plus 3 dy, right? Now along C2, remember we are moving in this direction, right? So along C2, x is equal to 2. Along C2, x is equal to 2. That means dx is 0. So everything in terms of y, right? Everything we can convert in terms of y. So we need to convert y varies from, and where is y varies from? Again, it varies from minus 4 to 4, right? So therefore, this will be integration over C2 x square minus 2xy dx plus x square y plus 3 dy. This will be, so since dx is 0, this term will be 0, and this will be y varies from minus 4 to 4, and we know x is 2, so this will be 4y plus 3 dy, right? This will be 4 times y square by 2 minus 4 to 4 plus 3 times integration of dy is y minus 4 to 4. This term will be 0, right? Because 4 square minus 4 square, this will be 0. So we will have 3 times 4 plus 4. So 3 into 8, so this will be 24. Therefore, integral over C m dx plus n dy is integral over C1 plus integral over C2, right? Therefore, the integral over C1 is 128 by 5. This is 24, right? 128 by 5 plus 24. So add up, you will get the answer, right? 128 by 5. Is there any term that we have missed? I'm not getting the answer. So actually, along C2, it is 24. So along C1, we are getting the answer to be 128 by 5 minus 24. Is there any mistake that we have made here? Okay, sorry, wait a minute. Here we have minus, right? This is minus here. Here you have minus, I have missed this minus sign here, right? Wait. This y power 5, right? Sorry. Y power 5. So here we have minus 1 by 16 into 5. Here we have 4 power 5. 4 power 5, right? Yes, sorry. So this will be minus 1 by 16 into 5. So this will be 2 times 4 power 5, right? 2 times 4 power 5. 2 times 4 power 5. This will be 24, right? This will be 24. So you can see this is 4 square. This is 4 power 5. So here we will have minus 1 by 5, 2 into 4 cube plus 24, right? So 4 cube is 64. 64 to 2 is 128. So we'll have minus 128 by 5 plus 24, right? Minus 128 by 5 plus 24, right? Square minus. Yes, right? Okay. So this is the area. Yes, minus 8 by 5. So this will be minus 8 by 5. So since it is area, so we'll take modulus of it, right? So this will be plus 8 by 5. Okay, so since it is area, we take modulus of it. So you will have 8 by 5 plus 24, right? So this will be 8 plus 120 by 5. So 128 by 5 is our line integral that we have evaluated, which is m dx plus n dy. Now we need to evaluate this, right? Now for LHS, now we need to evaluate integral over r dou n by dou x minus dou m by dou y dx dy, right? We need to evaluate this dou m by dou y, dou n by dou x minus dou n by dou y dx dy. Now, very easy to evaluate, right? So what is m here? M dx plus n dy. So m is x square minus 2xy. What is n? N is x square y plus 3. Right? X square y plus 3. So we need dou my dou y with 0 minus 2x into 1. So we will have minus 2x. And dou n by dou x will be 2x into y, which is 2xy, right? With respect to x, so y is constant. We are differentiating partially, right? So y into 2x plus 0, so 2xy. With respect to y, we will have minus 2x. Therefore, this will be double integral over r. Dou n by dou x is 2xy minus dou m by dou y is minus 2x dx dy. Now, we need to evaluate this. So, you can see x varies from we have x is equal to 2. Okay, what we'll do is we can do anything, right? You can treat x varies from 2 to x varies from 2 to y square by 8. You can treat y varies from minus 4 to 4, or you can also do like x varies from 0 to 2, y varies from minus 4 to root 8x. You can also do like that also. So here what I'm going to do is I'm going to vary y from I'm going to vary y from minus 4 to 4, and x varies from x varies from, so we can cover this. So x varies from 0 to y square by 8, right? Or you can also do like, actually you need to cover this entire region, right? You can also do like x varies from 0 to 2, right? X varies from 0 to 2. This also y, right? This also y square is equal to 8x. You can do like x varies from 0 to 2. It is your wish, right? You can take any. So what I'm going to do is x varies from 0 to 2. Y varies from root x to root 8x to minus root 8x, right? Generally you can cover this region as well as this region, right? That means this curve is actually y square is equal to 8x, means y is equal to plus or minus root 8x. So therefore this will be plus root 8x, this will be minus root 8x, right? So since we are taking x varies from 0 to 2, y varies from root 8x to minus root 8x to plus root 8x, right? So this is the limits now. Therefore, x varies from 0 to 2, y varies from um, minus root 8x to plus root 8x plus root 8x, 2xy plus 2x dy dx, right? First we are having y limits, so dy dx will be x varies from 0 to 2. So with respect to y, so 2x y square by 2 minus root 8x to plus root 8x, 2x integration of dy is y minus root 8x to plus root 8x dx. Now you can see this. So when you integrate this, you will have this 2 will get cancelled. Sorry, when you put upper limit minus lower limit, you will have x varies from 0 to 2, x into, yes, for double integral we need to cover whole, but for line integral, see, for double integral we need to cover this entire region, but for line integral we need to cover only this curve and this line. That line is also a curve, so this curve and this line, that is what it tells the relationship between this double integration over dou n by dou x minus dou m by dou y is same as the line integral this plus this. That's what Green's theorem says. So whenever we are doing this, we are covering this entire region, but for line integral we are only covering this curve plus this curve, that's it. So y square will be root 8x whole square is 8x minus again this will be 8x, right? So root 8x whole square is 8x. Yes. Here we will have 2x. So root 8 upper limit minus lower limit. So 2 times root 8x into dx. So this term will get vanished. So we have this to be equal to 4x. So let's take all the constants outside. So 2 to root 8. So 2 into root 8. So there are 3 constants. X into root x. 0 to 2. Right? This will be 4 times root 8 integration of x power 3 by 2 dx 0 to 2. This will be 4 root 8. So this will be this will be x power 3 by 2 plus 1 by 3 by 2 plus 1. So 4 root 8 x power 5 by 2 by 5 by 2. Limits is 0 to 2. So 4 root 8 into 2 by 5. So I've taken this 5 by 2 here. Here we will have 2 power 5 by 2, right? 2 power 5 by 2. So this will be 4 root 8 into 2 by 5. Can write this as 2 square into 1 by 2, right? It's 2 square into 1 by 2. Direction is correct, right? 2x y square by 2. So y square will be 0. So 2x root 2 4 root 8 x power 3 by 2 power 3 by 2 x 2 by 5. Okay. So 2 square is 4. So 4 into 4 is 16. Right? 16 into root 8 into root 2 into 5. Right? So root 8 into root 2 into 2 by 5. 2 by 5. So this will be 16 into root. This will be root 16 into 2 by 5. It will be 16 into 4 into 2 by 5. So 16 into 4. Okay, that's a mistake. So 2xy plus 2x dx. So with respect to y, so it is 2x, 2 times root 8x. I think I made some mistake anyway. So let's check this. Yes, yeah, I think I got the answer right. Sorry. So it is 64 into 2 by 5. 128 by 5. It's correct only. Right. So yes. Therefore, you can see this. So therefore, Green's theorem is verified. Right. So you can see both are 128 by 5, right? So this 128 by 5. This also 128 by 5. So both are 128 by 5. Is it clear? On the third problem. So move on to third problem. So verify Green's theorem in a plane for verify Green's theorem in a plane for integral over c 3x square minus 8y square dx plus 4y minus 6xy dy. Let C is the boundary of the region. Let C is the boundary of the region defined by x is 0, y is 0, and x plus y is equal to 1. Right? So we need to verify Green's theorem for this problem. So first we'll draw the diagram. Right? First we'll draw the diagram. So what is the boundary here? X is equal to 0. Right? So this is y is equal to 0. And this x is equal to 0. Right? And we have x plus y is equal to 1. So this is a line. Right? Therefore, this is the region now. Right? So this is y is equal to 0. This x is equal to 0. And we have x plus y is equal to 1. So what is the point of intersection? So when y is 0, x is 1. So this point will be 1 comma 0. And when x is 0, y is 1. So this point will be 0 comma 1. Right? So very easy. This is a line, right? This point is 0 because here it lies on x-axis. That means that y will be 0 If y is 0, what is x? X will be equal to 1 because this point lies in the line, right? So we have found the point of intersection. So we will have three curves. So C1, C2, C3. 1, C2, C3, or this is C1, C2, C3, right? You can take any order. So here you will have, let's call this as C1, call this as C2, call this as C3, right? So to evaluate line integral, so this plus this will give you integral over C m dx plus n dy, and we need to evaluate double integral also, right? So what we need to verify, so we need to prove double integral over R dou n by dou x minus dou m by dou y dx dy is equal to integral over C m dx plus n dy, right? So first we will find the RHS part. So integral over C m dx plus n dy is equal to integral over C1 plus C2 plus C3, right? Integral over C1, integral over C2, integral over C3, C1, C2, C3. Now first we will do along C1. Now along C1, y is 0, right? Along C1, y is 0. So dy is 0. Everything in terms of x. So x varies from, so this point is 0, 0. X varies from 0 to 1. Right? Therefore, integral over C1 m dx plus n dy will be integral over C1. So x varies from 0 to 1. 3x square minus 8y square dx 4y minus 6xy dy, and dy is 0, this will be 0, y is 0, this will be 0. So we will have 3 times integration of x square dx, x varies from 0 to 1. So 3 times x cube by 3, x varies from 0 to 1, this will be 1, right? So along C1, it is line integral is 1. Now along C2, you can treat y varies from 1 to x, or x varies from x is equal to 1 minus y. That is your wish. So along C2, what I'm going to do is, let us along C2, x is equal to 1 minus y. I'm converting everything in terms of y. Or you can also convert everything in terms of x also. So that means what is dx? What is dx by dy? It is 0 minus 1. It's differentiate with respect to y. That means dx is equal to minus dy. So I'm converting everything in terms of y. That means we need to find y limits. So y varies from year to year, y varies from 0 to 1. Right? You can also convert you can also write y is equal to 1 minus x. You can convert everything in terms of x also, right? Okay, this is your wish. So integral over C2 m dx plus n dy will be integral over C2. So y varies from 0 to 1. What is the problem? 3x square minus 8 y square into dx plus 4y 6xy dy, right? Check the question once again. 3x square minus 8y square dx plus 4y minus 6xy dy. Yes, okay. So dx is minus dy and x is 1 minus y. So y varies from 0 to 1. So 1 minus y whole square minus 8 into y square dx is minus dy. 4y minus 6x is 1 minus y into y dy, right? So you need to evaluate this integral. So this will be integration of 0 to 1, 3 into 1 minus a square minus 2ab plus b square minus 8y square dy. And this will be integration of 0 to 1, 4y. So minus 6y plus 6y into y. So you'll have plus 6y square dy. So this will be integration of 0 to 1, 3 minus 6y plus 3y square minus 8y square dy. And then this will be integration of minus 2y plus 6y square dy, right? So here y varies from 0 to 1. To perform this integration, so 3 times integration of dy is y minus 6 times integration of y is y square by 2. Here you will have minus 5y square, minus 5y square will be y cube by 3, and here you will have minus 2 times y integration of y dy is y square by 2 plus 6 times y cube by 3, right? Everything y varies from 0 to 1. So 3 minus 6 by 2 minus 5 by 3 minus 1 plus 6 by 3. So this will be 3 minus 3 minus 5 by 3 minus 1 plus 2. So this will be minus 5 minus 3 by 3 plus 2 minus 8 by 3 plus 2 minus 8 plus 6 by 3 minus 2 by 3. This will be 2 by 3, I think. So 3x square I need to multiply this minus inside, right? So here we have minus dy, but when you're writing this, I written this as dy. Okay, let us put this minus here, right? Yes, we have minus dy, right? Let's put this minus here. So therefore, we will have minus of these three terms. So this will be minus, and this will be plus 6y. This will be minus so let's try to do like this. So 3 plus plus 5 by 3 yes. So this will be 5 by 3 plus 1, right? 2 minus 1 is 1. So this will be 8 by 3. So 8 by 3 is our 8 by 3 is our along C2. Now along C3, here we have minus dy, right? Written this minus here, right? Written this minus here. So along C3, so you can see along C3 x is 0, right? So along C3 x is 0. So that means dx is 0. So everything in terms of y here, right? Because in integrating x and the dx term will get vanished. And that is in this here, mdx plus ndy will be integral over, what is the question? 3x square minus 8y square dx plus 4y minus 6xy dy, right? So here x is 0, dx is 0. So dx is 0, x is 0. So we have everything in terms of y. That means y varies from, so where is y varies from 1 to 0, right? Remember direction is important. Y varies from 1 to 0, right? 1 to 0. Y varies from 1 to 0. Y varies from 1 to 0. Therefore, y varies from 1 to 0. So we will have only we will have 4y dy. So 4y square by 2, 1 to 0. This will be 2. This will be 0 minus 1. This will be minus 2. So therefore, integral over C mdx plus ndy is integral over C1, integral over C2, integral over C3. So what is C1? C1 is 1. This is 8 by 3. This is minus 2. So 8 by 3 minus 1 will be 5 by 3, right? 8 minus 3 by 3. So 5 by 3. So 5 by 3 is our line integral mdx plus ndy. Remember the problem is not over, right? We need to find double integral over r dou n by dou x minus dou m by dou y dx dy, that we need to find out, and we need to show that is also equal to 5 by 3. Now we need to find this, right? So now double integral over r dou n by dou x minus dou m by dou y dx dy, right? Dou n by dou x minus dou m by dou y dx dy. So what is m here? M dx plus n dy. So 3x square minus 8y square. What is n? N is 4y minus 6xy. 4y minus 6xy. So dou m by dou y will be 0, be 16y. So minus 16y. Dou n by dou x should be minus 6y. So therefore, this will be double integral over r dou n by dou x minus dou m by dou y dx dy. So double integral over r plus 16y minus 16y. This will be 10y dx dy, right? 16y minus 6y is 10y. Okay. Now, very easy to do this, right? So we need to cover this entire portion. So y varies, x varies from 0 to 1, right? Y varies from 0 to 1 minus x. So x varies from 0 to 1. Y varies from 0 to 1 minus x, right? So we can cover this entire region. So this okay. So therefore, x varies from 0 to 1. Y varies from, yes, hello, good morning. Yes. Okay. So this will be x varies from 0 to 1 and y varies from 0 to 1 minus x, 10y dx dy dx, right? Y dy dx. Let this 10 outside. X varies from 0 to 1, and this will be y square by 2, 0 to 1 minus x dx. 2, this 10 will get 5. So 5 varies from 0 to 1, 1 minus x square dx. So this will be 5 times integration of a square plus b square minus 2ab. Here we have dx. X varies from 0 to 1. So 5 times integration of dx is x, 0 to 1. So this will be x cube by 3, 0 to 1. Will be x square by 2, 0 to 1. So 5 times 1 plus 1 by 3 minus 1, right? So these two will get cancelled. So we will have this to be equal to 5 by 3. Therefore, this also 5 by 3, this also 5 by 3. So therefore, Green's theorem is verified. Very easy, right? So since we already discussed line integral and you already know how to evaluate double integral, evaluating this integral is very easy, right? Evaluating this integral is easy. That is what I have said many times when we are doing line integral, surface integral, volume integral. Listen this very carefully. Then the next 3 theorems will be very easy for you if you know how to evaluate these line integrals and so on, right? That is what I have stressed. Okay, so in the next class, we will continue more problems on Green's theorem. So I'll give you lots of practice problems for Green's theorem, right? So in the next class also, we will continue more problems on Green's theorem, right? So next class, it will be a lengthy class because in the next class, you will try to complete Green's theorem. So next class will be a lengthy class. It may go for 2 hours also, right? It may go for 2 to 2.5 hours. So by next class, we will be completing Green's theorem, right? In next class. Okay. So that's it. Next class, we will continue some problems. So I think there will be no doubt. If you haven't joined Telegram group, join that. And if you haven't downloaded our app, download our app. This link is in the description, right? Okay. So thank you. Bye.